Okay, my name is Kevin McIntyre from the Jones Center at Itchaway. I'd like to welcome you to our webinar today featuring Dr. Stephen Brantley. Stephen's talk is on optimizing ecosystem services from longleaf pine, balancing carbon sequestration with watershed health. I'm going to go through a few introductory slides here, and then I will hand things over to Stephen. Okay, most of you are probably interested in continuing education credits from your experience here today. So there's 4 things that you have to do to receive your continuing education credits. First, you need to complete the satisfaction survey, take and pass the short quiz, number 2, and 3, complete the continuing education unit request form and certify finally that you have participated in the webinar in its entirety. All of these things can be found on the webinar portal. Here's the page you need to look for the CEUs. No partial credits, and there will be recordings available. If you have any questions, please contact SREF at the web address listed below. We will ask you to give us any questions you may have using the Q&A feature on Zoom, not so much chat. We will take questions at the end of the webinar and answer as many of them as we can. And of course, if you don't already, please subscribe to the webinar portal to learn about upcoming webinars. The address is there. And again, thank you for joining us. I'm going to get Stephen to share his screen, and I'll stop sharing mine. This information will be posted up at the end of the webinar too. So thank you again for joining us.
Are you ready for me to share?
Yes.
Okay. How does that look, Kevin? Are you seeing the correct view?
Looks great.
Okay. Great. Well, thanks everybody for coming today. If you're in Louisiana or Mississippi, thanks especially. It probably means you have power, so be grateful about that. I'll actually touch a little bit just in one slide later on hurricanes, because they actually play a role in some of the things that we're talking about today. So what I'm going to talk about today is sort of a balance of ecosystem services, but I'm going to focus mainly on watersheds and water as an ecosystem service that I focus on, that I think we can put a little bit more emphasis on in the Southeast than we do, and how that sort of balances against carbon sequestration, which is something that we all hear about, and it has some other benefits in terms of the fact that carbon sequestration shares some qualities with what we typically think of in forestry in terms of optimizing tree growth and production or productivity. So that's where we're going today. I want to do the acknowledgments up front. First, thank some key people. Steve Gallaudet and Stribling Stuber. Steve is an aquatic biologist that I work with, and I think the fact that I work most closely with an aquatic person will make sense later in the talk. Stribling Stuber is my lab manager. Jill Key is was a postdoc here that did some modeling work that I'll touch on. Seth Younger and Jeff Cannon. Seth is actually picking up on some of Jill's modeling work, and I'll touch on the project we're on with them later. And then a whole host of people that have contributed either directly or indirectly to this talk. And then lastly, Kevin McIntyre for giving me the opportunity. So thank Kevin. And then funding for all of what you see here was provided by a number of sources, but key among those was the Woodruff Foundation that funds the Jones Center. The NRCS through the SEAT program is a funding source that we're working with right now. And then some of this work in the past was funded by the Georgia chapter of the Nature Conservancy. I do want to clarify that some of the opinions expressed in this talk are my own professional opinions and don't necessarily reflect things that some of these funding sources might want to hear. an outline for the talk, I want to go over some key terminology. I want to talk about forest restoration as a water conservation strategy. Again, that's my professional focus, if you will. So to do that, I'll talk about some water budget basics, why longleaf pine would benefit water quantity, and how much benefit we think we can get from forestry practices in general, but from restoring longleaf pine. And then I'm going to finish off talking about balancing that water conservation with other ecosystem services. And I'll touch on some things that we hear about a lot, like water quality, wildlife, and economic benefits, just very briefly. And then for the rest of the talk, talk about carbon sequestration and how I think our perception of longleaf pine may be a little imbalanced. So some key terminology. I know when you start running through definitions, this can be a place where people kind of nod off. So it's early in the talk, don't nod off yet. But some things I want to clarify real quick before I get into the talk, and I'll touch on these in more detail as we go through. Ecosystem services, these are basically benefits that humans derive from nature. Sometimes they're very hard to quantify. Sometimes you can put a dollar value on them. Water quality, that's just the cleanliness or the drinkability, so to speak, of water, or how much treatment you have to do to it to get it to a place where it's safe to either consume or apply to crops. Water quantity, that's mainly what I focus on, is the amount of water that we can get from a watershed. And that has a couple of components or a couple of different terms that we can use. Runoff is what we think about in terms of streams and rivers and how much flow actually comes out of a watershed. And recharge is how much goes into groundwater without necessarily coming out through a stream or river. And then water yield is a term that I'll defer to quite often. Water yield is basically the total runoff or recharge in a watershed divided by the area of the watershed. And so you end up with a linear unit that you can compare to precipitation. So we'll talk about getting 10 inches of water yield or 12 inches of water yield. Evapotranspiration is basically the natural use of water by an ecosystem. So transpiration is what's used by plants. Evaporation could be evaporation from surfaces, whether that be plant surfaces or soils or even man-made structures. And that's similar to water consumption. And I'll come back to water consumption later, but water consumption is basically the total use of water by the watershed, not necessarily the uptake of it. Some water is taken up and then returned, say what you use in your household. Not all that is consumed, it's simply cycled. And so when I talk about consumption, I'm talking about water that's actually used by the ecosystem and evaporates away. And then carbon sequestration, this is something that gets a lot of press today, especially if you're in forestry. Basically the intake and storage of carbon by an ecosystem. And then lastly, something that connects carbon sequestration with water consumption is water use efficiency. And usually that's considered either the productivity of a forest per unit water used or the carbon intake of a forest per unit water used. And so I'll talk later on a little bit about water use efficiency versus water consumption. But with that sort of fire hose introduction to terminology, I wanted to touch a little bit on ecosystem services real quick. And if you're not familiar with ecosystem services or you're not familiar with the concept, I would suggest you check out the UN Millennium Ecosystem Assessment. And this figure is pulled directly from there. But again, these are benefits from ecosystems that ecosystems provide the human, and they can be everything from building material and food and water, as you see in the provisioning services. I'm not sure if you can see my cursor, but ecosystem services are often categorized in these 4 types: supporting, and then those build up to provisioning, regulating, cultural, et cetera. And then this figure shows a bunch of arrows about how these different ecosystem services support human well-being. The arrows that this figure don't show are arrows of how these ecosystem services interact with one another. And I think this is something that gets overlooked because it's important to realize that if we're managing ecosystems, we can manage ecosystems for one thing very well, but we may not be able to manage it for multiple things very well. In other words, if we're managing an ecosystem for food, we might plant a cornfield, and that cornfield might not be so good at regulating floods or reducing disease or purifying water. So there are trade-offs between ecosystem services, and I think that can get overlooked sometimes. So again, my focus is water, and so I want to go a little bit over how we think about the water budget in terms of a provisioning ecosystem service. And the equation for this is very simple. Runoff is usually what I think about because I again, work with a stream biologist. Runoff equals precipitation minus evapotranspiration. So it's basically just an input minus output equation. In our system, at least in most of our system, precipitation is the major input. We do have parts of our watershed that we work in where groundwater is very important. But for instance, in our watershed, groundwater, while it's a little bit more stable, it's not a long-term groundwater source, or water cycles through our groundwater system a lot faster. In some other systems, like in the California Sierra, snowmelt tends to be a very important input. And that's been disappearing out there, but I'll let you read more about that outside of this presentation. But those inputs are balanced against some simple outputs. Total output is evapotranspiration, and that usually is thought of with two components: transpiration, which is what plants use, and then interception, which is rainfall that comes in and is taken up or lands on surfaces. Could be leaves, could be stems, could be asphalt, and it simply evaporates back to the atmosphere. And so we measure these things in a variety of ways. Of course, climate stations and USGS stream gauges provide us a lot of data where we can estimate evapotranspiration if we know precipitation and runoff. If we want to know a little bit more about evapotranspiration, you see in the bottom left, there's an eddy flux tower that can measure evapotranspiration of a whole forest. Or one of the things that I've spent a lot of time on is working on transpiration of trees and measuring transpiration through sap flow. Now, yield or water yield, or sometimes called watershed yield, is that total runoff, so the balance again between precipitation and evapotranspiration, divided by watershed area. And so you'll see a lot of results in hydrology that talk about water yield. Water yield can vary tremendously from year to year. It varies with the inputs and outputs. So precipitation can be up and down. Obviously, we're in a very wet year here in Southwest Georgia. We're seeing more and more variability as time goes on. We're seeing drier growing seasons, longer, more severe droughts, but precipitation varies a lot. Evapotranspiration also varies. The going trend now is that evapotranspiration across the world is going up. In Southwest Georgia, irrigation certainly plays a role in that. In dry periods, irrigation demands a lot of water. We have a lot more irrigated acreage than we used to, so that's gone up. Warmer temperatures from climate change cause evapotranspiration to go up. And other things like increased urban consumption, again, not necessarily urban withdrawals, but actual consumption. But also changes in forest management over the last, let's say 30 to 50 years have caused evapotranspiration to go up. And I'll point out more about that when I talk about longleaf pine and why longleaf pine might be a way to curtail some of that. But with this variability, it's caused some general trends in water yield that they've been lower in recent years, at least in the Flint River Basin where I work in Georgia, but throughout much of the Southeast, especially Western United States, and even in the Southeast, though, we've seen some critically low water yields in certain years. So that brings up sort of the context of why I'm here and why I do what I do. Came to the Jones Center in 2014. We were really in the midst of what we call the water wars then. If you're not familiar with it, this was a legal battle that culminated in a recently decided Supreme Court case, but it involved basically two parties. One was oystermen in Apalachicola Bay, which is down here on the Florida Panhandle, and then water users in Georgia, and to a lesser extent in Alabama, with the two big parties being agriculture, so center pivot irrigation, which I'll touch on in a minute, and then also the explosion of urban centers like Atlanta and how they were withdrawing tremendous amounts of water from the Chattahoochee River. The Flint River is a river that's east of the Chattahoochee. They're all in the ACF Basin. The Flint and the Chattahoochee join to form the Apalachicola at the Georgia-Florida line down here. But the Flint was more impacted by agricultural use, and Atlanta is what tended to be blamed, at least, for affecting flows in the Chattahoochee. And the case was recently decided. It was a unanimous decision against Florida, or for Georgia, if you want to take that perspective, that Florida hadn't proven its case that what Georgia was doing to manage water was bad for the oyster industry in Apalachicola Bay. So that's sort of a context. I try not to take sides on this, but provide solutions. So I'm gonna try to start talking about some of that now. Water consumption in the ACF Basin. Well, agriculture, just to cut to the chase, was and is the dominant water user. It's concentrated in the lower basin on the Flint River side of the basin. And this is a result of development that's been happening since the mid 1970s. Tremendous consumption of water, and one of the negatives is that the consumption tends to be in drier years increases. So when you go into a drought to maintain crops, there's actually more and more irrigation. And so we worked on this through a contract with the Georgia chapter of the Nature Conservancy. And what they wanted to do was evaluate some of the agricultural conservation measures that they had put in place or helped put in place over the years. And there's a number of these things like low pressure drop nozzles and in-gun cancellation and smart irrigation. And so we worked with them to do a study where we simulated how irrigation reduction improved low flows in the Itchaway-Nottoway Creek, which is a major subbasin of the lower Flint. And it seemed to work pretty well. But like a lot of you, I think our main interest still was in forestry and how forest could be used as a management tool to help manage water yield. So if we look at land use in the Itchaway-Nottoway Creek Basin, we see that, yeah, there is a lot of agriculture, but it's actually maybe a little bit less than you would think. It's only about 28% row crop. And then there's a lot of pasture, which is not irrigated. Some urban. This is a very rural area, though. But 48% of the Itchaway-Nottoway Creek Basin is forested. However, only a fraction of that forested part of the basin is in longleaf pine. And longleaf pine was the reference ecosystem in this area. It once covered maybe up to 80% of this watershed. And now it's been supplanted largely by either fire suppressed mixed pine hardwood forest or by what I'll call plantation pine. And these tend to be the short rotation loblolly or slash, in some cases, very dense pine plantations that are grown up for productivity, for production, whether that be for paper mills or for other wood products. And so we looked at this mix of land covers in this basin and asked the question, can forest management provide another tool to help us manage water yield? And primary among that question was, is longleaf pine the answer to this? Can we, by changing the forest landscape mix to be more heavily balanced towards longleaf pine, which was, again, the historic condition of the watershed, can we improve water yield? So why might longleaf pine benefit water yield? Really, the main key is the density. It's more of a woodland type ecosystem. It has lower density of trees, lower leaf area, lower basal area. And simply put, when you have fewer trees, those trees are going to use less water. Now, there's a little bit more to it than that, but that's the fundamental answer right there. You do have some lower per tree transpiration in longleaf, than slash or loblolly pine. That's not universal. That can vary by site, but we do see some trends where longleaf pine typically responds to drought by downregulating how much water it uses or using less water, whereas a lot of other species will either just maintain their water use through drought or actually, in some oaks, actually try to use more water. Prescribed fire helps to suppress mid-story growth. Of course, prescribed fire is important for longleaf for many other reasons. It maintains the entire ecosystem, but prescribed fire helps basically maintain a warm season grass layer in many areas, not in all areas of the longleaf range, but warm season grass understory ends up having both a higher water use efficiency. In other words, its growth per unit water used is very high. And I'll show you a comparison of that in a few minutes. And it has a lower leaf area. So what you see out here in this shot of this savanna might appear to be quite a bit of leaf area, but a lot of that's dead or dormant leaves from the year before mixed in with leaves that maybe have gone past their prime. And so if you look at actual live leaf area in the understory, it's actually relatively low compared to if you had an understory of mostly shrubs and young trees. So the result of all these structural characteristics of longleaf is that evapotranspiration is lower than really any other forested or any other vegetated land cover type in the Southeast. Stand level evapotranspiration, or ET, is only about 70 to 80% of what you would see in slash or loblolly pine in a typically managed loblolly plantation. And when you reduce evapotranspiration, of course, your water yield goes up, all other factors like precipitation being equal. So how do we test this concept? We use simulation modeling. We used a tool called SWAT, which is a soil and water assessment tool. This is a process-based model, meaning that it's not simply derived from statistics, but uses physical characteristics of the watershed. We input climate variability like rainfall and temperature, radiation, and also stream flow data is what's used to calibrate the outputs against. It uses soils. This is basically a curve number model. If you're familiar with basic soil hydrology. So we have a soil layer in there. Topography, not a lot of topography in this basin. I think it's averages 0 to about 5%, but topography can be important in other basins. And then land cover. And land cover is one, that's really the parameter that we were most interested in manipulating. So land cover could be different types of forest, how those forests respond to different types of environmental parameters. So for us, we were interested in comparing your dense pine plantation to a typically managed loblolly, or I'm sorry, longleaf plantation. So higher density versus lower density, trees that respond to drought versus trees that may not respond to drought as strongly, a grassy understory versus a understory that isn't there because there's too many trees there. And we can manipulate all those things within the SWOT model by creating a new land cover that represents longleaf pine. So how important was longleaf restoration for stream flow? We wanted to push the envelope to see an effect. So we converted 230,000 acres of forested land in the watershed to longleaf pine. So we increased longleaf cover from 4% to 35%. We basically didn't mess with any farmland. We didn't mess with pasture land. We didn't touch wetlands for other reasons. We just looked at those two land cover types, the mixed hardwood pine, which could in some cases be relatively easily converted to longleaf, and to loblolly pine, which might be a little harder to convert, but we wanted to see what would happen. So modeled evapotranspiration decrease is expected, decreased by about 4% in general. Annual water yield increased by 9%. And to put that in stream flow terms, for the Itchway-Notchaway Creek Basin, that was a difference of 53 million cubic meters of water per year. And so that's a fairly substantial effect. But I think what we were more excited about was that these changes were most pronounced during periods of extreme low flow. So if you look at this upper part of the graph, or upper left panel, you'll see the absolute change in total yield in the black circles, and then the white triangles is the relative change. So this is on an annual basis, and it's compared against precipitation. So in years where you had only between 900 and 1,000 millimeters of precipitation a year, I think that's, if I'm doing the math right, less than about 40 inches of rainfall. You saw a relatively small change in absolute yield, but up to 15 or 16% increase in relative change. And then that change goes away a little bit. The relative change goes away when you get into wetter years, which is fine. That's not a time when we necessarily want to increase yield. If you look at it on a seasonal basis, it's interesting. Oftentimes the worst drought effects that we see are in late summer and early fall. And what we saw about changing land cover to longleaf pine was that in October, when we typically see our lowest values for water yield, we saw up to about a 50% increase in stream flow, which is just really substantial. So we're very happy about that. That's not a lot of water from an annual yield standpoint. It doesn't take a lot of water to make that change because water levels that time of year are already very low. But that could mean that could have huge benefits for aquatic habitat. Again, these are times of year, September, October, when streams tend to be at their lowest, and aquatic fauna, like fish, shoal bass is something we're very interested in down here. Mussels tend to be most vulnerable. So seeing that big increase in October, we were very pleased with. Now, that's one study. We're actually in the final phases of revising that study and resubmitting it for peer review. We do have some ongoing research though. And some of that, we're looking from an aquatic standpoint at seeing how important that water yield is to the aquatic systems. Some newer research on the terrestrial side of things, funded by NRCS and their SEET program. We're trying to test the same concept in other watersheds, again, through simulation modeling, and also trying to simulate real world forestry conservation practices. I think one of the weaknesses of that previous study was that we basically took land cover that was one type and overnight changed it to longleaf pine. And of course, we know that that's just not the case. There are going to be cycles, there's going to be harvest, there's going to be replanting, or there's going to be underplanting, and maybe a period where a landowner might want to rake straw or use the longleaf for some other use to recoup cost. So we're trying to look into simulating some of the real world conservation practices to make this modeling more realistic. And then also wanted to plug real quick some other research being done by the Forest Service at Santee Experimental Forest, where they're actually doing a paired watershed manipulation, where one watershed is being left as a reference loblolly dominated watershed, and they're changing another watershed to be dominated by longleaf pine and monitoring how that actually affects water yield over time. And the only downside of that is it's going to take several years to get results. That's where simulation modeling has an advantage. But I think in the long term, that's going to be extremely valuable for us to know without a doubt that this type of management has an effect. So with that, I hope you're convinced that we can benefit from restoring longleaf pine from a water quantity standpoint. I do want to talk for a minute, though, about balancing that water conservation strategy of forestry with other ecosystem services, because we can't all live in a bubble and we can't all just manage our forest for water yield. So what are some downsides to longleaf pine? And I'm framing this mainly as a way to answer some questions that I've gotten in the past from various folks who are concerned that if they go towards longleaf pine, that they might lose out. So one question oftentimes is water quality. Longleaf is usually as low as a third of the density of other forest types in terms of tree density. But I want to assure you that longleaf, as far as we know, has the same water quality benefits as any other forest type. It prevents erosion, it helps to build soil, these forests assimilate nutrients. And although there's some short-term effect on water chemistry of prescribed fire, it's really not a lasting effect and likely has very little, if any, negative connotation. And this is something that's been studied surprisingly little. We do have a USDA grant now where we're studying the water quality of wetlands, geographically isolated wetlands on Jones Center. So it's embedded within longleaf pine, and the water quality differences between this and a farm just off site are just tremendous, as you might expect. But I really don't think there's any water quality downside to longleaf pine. Another question we'll get oftentimes is about wildlife. I think it's well known that longleaf pine has huge benefits for certain endemic wildlife. A lot of longleaf pine stands today are managed for red-cockaded woodpeckers. Gopher tortoises certainly are a known species that benefits. That's a rare plant called Schwabia on the right-hand side that exists only around the margins of longleaf pine embedded wetlands. So from an endangered or rare plant standpoint, plant and animal standpoint, longleaf is a great solution for the Southeast. And then from a more of a game standpoint, of course, longleaf wouldn't probably be here today if it weren't for bobwhite quail and a lot of the early plantations that maintained longleaf for quail hunting back in the early 20th century. But some people are concerned that longleaf may not be the best habitat for other game species like deer or turkey. And I think that's something that you might hear about next month when my colleague Mike Connor talks about wildlife. But I can assure you from my experience, these are a couple of shots on the lower left of turkeys and deer from the same trail camera. And there's just an abundance of wildlife in this ecosystem. A lot of people are concerned about spring burning, destroying turkey nests. Again, I don't think there's any population effect at all. And in terms of productivity for species like white-tailed deer, it's tremendous. It's tremendous potential. And I was told when I was given these pictures to point out that that white spot on the lower right of these photos was not a corn pile. It's actually a gopher tortoise apron. So we're not stoking the pictures and fixing things just to make you think there are a lot of deer and turkey. They're really out there. So wildlife, again, huge benefit for wildlife from longleaf pine. One real downside potentially is cost. And this can come in a variety of ways. I'm not an economist, but I'm sure there's a lot of people out there that probably know more about this than me. But certainly operational costs come into play. It takes a pretty well experienced crew to be able to burn longleaf pine every other year or every third year. So these are some guys from our conservation staff here on their ATVs getting ready to light up a burn unit. So that's a real cost. And there are ways to get help from that with different government programs that I'll let you all look into if you're interested. And then opportunity cost. There's certainly a lost opportunity cost. When you're talking about longleaf pine, you're not talking about a species that's going to grow up to maturity in 20 or 25 years and be harvestable in that short time frame. So we do recognize that there are costs in terms of making a long-term investment that you as a landowner might not even see in your lifetime. And then lastly, what I want to focus on though is the carbon sequestration and storage question. And I want to ask the question, does the combination of low tree density and regular prescribed fire reduce the ability of longleaf to take in and store carbon? And here's two examples. One of, again, of that same dense pine plantation forest with a lot of above ground biomass in it. And then a longleaf system with a lot less biomass in it, both in the canopy and on the ground. So there are real differences between these ecosystems that I want to address. And the unequivocal answer is, does this type of management affect carbon sequestration? And the answer is an unequivocal, it depends. So on a short term, does longleaf sequester less carbon? Yes, it does. Longleaf takes in less carbon in a given year than just about any other forest type in the Southeast. And yes, prescribed burning converts a substantial amount of biomass in the system to CO2. I think we get a lot of our information about carbon sequestration from data sources that really focus on the short term. So for instance, on the right here is the Eddy covariance tower that measures total intake of carbon and output of carbon and can give you a balance of what the ecosystem is really producing. And then you combine that with estimates of fire fuel consumption and how that's converted to CO2. And you can see in some years, longleaf pine forest can even be a carbon source. But that's a very short-term perspective. And unfortunately, it has dominated some of the management circles in terms of deciding what to plant to sequester carbon. So I want to take a little bit of a long-term perspective. Well, long-term, first of all, more carbon is stored below ground in roots and soils than above ground anyway. I see conservative estimates in some of the accounting practices that say 50% of carbon in the ecosystem is stored below ground. I think that's actually on the low side. I think it could be more close to 70, 75, 80%. Certainly depends on the ecosystem. But I think a bigger issue is that when you clear cut harvest a stand of, say, loblolly that's been churning away, producing wood and taking in carbon for the last 20 or 25 years, you also release a huge amount of the carbon that's been stored up in that soil. Enough that over time, over a couple of these cycles, you can actually deplete soil carbon by using that fast rotation approach. Whereas in a longleaf system, if you use an ecological forestry practices where you're only taking a certain number of the trees, so you're harvesting, say, 5% or 10% of the tree biomass every 5 or 10 years, you can maintain that carbon in the soil. You're not doing as much disturbance, and you're not increasing the soil respiration by causing more light and higher temperatures to affect that soil respiration. So I think from a long term, what you're seeing with longleaf, even longleaf that is harvested in an ecological way, you're going to see a buildup of carbon in the soil. Whereas with a shorter rotation schedule, you're going to see a lot less carbon in the soil over time. Another long-term effect of longleaf, you may have heard this before, but the idea that burn now or burn later. Of course, we burn here at Jones Center every 2 years. Some places might be 3 years, 5 years, 7 years. But we know that by burning consistently and releasing a little bit of carbon, that we prevent the kind of catastrophic loss that you're seeing, for example, right now out in California. And I show this screenshot that I took last week from the CAL FIRE website about some of the big fires that are going on out in California. Over 700,000 acres of ponderosa pine in the Dixie Fire. I think it's ponderosa, it may be something else, I forget. The Caldor Fire came to my attention specifically because my brother lives 6 miles south of the fire line right now. And so thankfully it's moving in the opposite direction of his home. But he told me that the ridge that he lives on hasn't burned in 100 years. And so it's basically a tinderbox. So from a carbon standpoint, burning regularly actually is going to reduce your long-term carbon footprint by reducing that catastrophic loss of fire that would happen if you waited 100 years and the entire forest went up in flames. Other issues you might see comparing longleaf to loblolly, of course, insects certainly might get your trees. Longleaf has a well-deserved reputation as being fairly impervious to insect damage. Again, I'm not the expert on this, but I think if you look through the literature on longleaf, you'll see that it's quite a bit more resilient to insect disturbance than a lot of the other pines. And then another disturbance that really came close to us 3 years ago, and I'm thinking about now happen in Louisiana, is that a storm might get your trees. And again, longleaf has a well-deserved, it looks like, reputation in terms of being able to withstand storms a little bit better than loblolly or slash. It's not impervious. I want to make that clear. Longleaf is not impervious to wind damage, but there is probably enough difference between loblolly or longleaf and loblolly and slash that it could make a difference long term in terms of carbon sequestration and even wood production. And I meant to mention this was Hurricane Michael from October 2011, right before it hit, and came through and absolutely decimated forest in the southeast. So maybe in 3 years, I'll be showing a picture of Hurricane Ida. And getting towards the end of this sort of shotgunning of reasons that longleaf is great for carbon, I wanted to share this paper that was led by Bob Mitchell and a bunch of folks associated with Itchaway a few years ago about how applying the Climate Action Reserve's protocol to longleaf pine that was being restored really brought up some issues with the way accounting of carbon programs how it works. And so I use this little cartoon. This cartoon is usually used from a social justice or equity point of view to show that, if you design a test a certain way, you're basically biasing it towards a certain outcome for certain individuals. And so I think the analogy here is that what we're saying is that the tree in the background that the examiner is asking all the animals to climb, that's carbon sequestration. And he's asking longleaf to climb in a way that maybe doesn't suit its strength. You know, sequestering carbon on a rapid basis is something that is very good if you're testing out loblolly. Loblolly and slash are some of the most productive ecosystems in the temperate zone, given the right climate. But I think what we're doing is putting longleaf up against a reference condition that it was never really meant to be compared to when we start talking about longleaf pine and its carbon sequestration potential in the short term. So don't just listen to me about this. Again, I fully admit that I'm biased towards water. But I'll ask some questions that I want you to think about. One is forest carbon sequestration the solution? In the United States, all the carbon taken in by forests in a good year is only about 12% of what we emit. I think we're conflating geological carbon, that being from fossil fuels, to biological carbon. Those are two different cycles that we're trying to see match up with each other. We're looking at whether or not carbon offsetting actually reduces carbon emissions. I think in some cases it does, in some cases it doesn't. Certainly if you have a forest that you want to protect to keep it from becoming a strip mall, I think that's a good thing. But if you have a forest like we have here at the Jones Center or some other conservation areas, and you want to put that into a carbon offsetting program, somebody's going to buy that and use that as a reason not to reduce their carbon emissions. And so are you really doing, in the long run, the climate any good? There are certainly questions about biofuels not being carbon neutral, or at least, there's certain situations where they are or aren't. Poor accounting practices, whether that be below ground accounting or other, what your reference condition is. But I'll leave you with this list of different articles that I've been reading up on over the last few months. Some of these are from great sources like nature.com and the Water Resources Institute, and EOS, which is an AGU, American Geophysical Union publication. And some are from sources that might be a little bit more questionable, like theverge.com. But I do think that they actually did a pretty decent job in referencing and laying out an argument about some of the weaknesses of forest carbon offsets. And then lastly, just to come full circle and link carbon and water again, I want to talk just real briefly about carbon sequestration and water and talk about efficiency versus consumption. Of course, I've mentioned before, efficiency is the amount of growth or carbon intake per unit of water used. And so we hear about very high levels of water use efficiency in some grass species or in some tree species. I think all the pines have a high carbon water use efficiency. Eucalyptus has an even higher water use efficiency, depending on who you read. But there's more to it than that. And what I really want you to focus on is water consumption, and that's the total water used. And if you look at the two pictures here, there's a couple of technicians from Itchaway looking at wiregrass, and then there is a grower growing miscanthus or switchgrass for carbon sequestration. These two species, wiregrass on the top and miscanthus on the bottom, have about the same water use efficiency. But think about it, which one do you think is using more water? If you take in a lot of carbon, you're going to use a lot more water, whether your efficiency is very high or very low. Just something to be aware of when you hear the term efficiency thrown out. So just to summarize, water shortages in the Southeast are only likely to get worse, and restoring longleaf can be part of that solution. It's not all about agriculture. It's not all about growth of cities. It's about forestry and forest management, reintroducing prescribed fire. In total, longleaf provides a great suite of ecosystem services. Not only does it increase water yield, but it's great wildlife habitat. It has super aesthetics and cultural value, and it is a good source of long-term carbon gain. So I wanted to share a quote, or sort of a paraphrase quote, from a forester that I respect a lot, and that's Jerry Franklin. And he's basically said this every time I've met with him, that management that optimizes any single ecosystem service, like carbon sequestration, will almost always reduce the provision of other ecosystem services. And it's just something to think about in terms of what your goals are and what you want to do as a manager. And I'll leave you with the fact that, yeah, the need to sequester carbon is important. I'm not denying that at all. We're putting way too much carbon into our atmosphere, but those needs need to be assessed critically and carefully, and also consider regional needs and the trade-offs with other ecosystem services like water yield. With that, I'll remind you to go to this page to obtain your CEUs. I can come back to this in a few minutes. I'm a presenter, so I'm not necessarily equipped to answer a lot of those questions, but there are people on the call that will be. But I can come back to that page if needed. And then also just wanted to plug again, subscribe to the webinar portal to learn about more upcoming webinars like this one. Whether you enjoyed this one or absolutely hated it, I'm sure that there's some other talented speakers out there that you might enjoy listening to. And with that, I'd like to take any questions.
Thank you very much, Stephen. We do have a few questions lined up for you. First of all, from Jay Jensen. Hey, Jay, thank you for joining us today. On your carbon sequestration slide, can you give us an approximate range for what you're talking about in terms of long-term for carbon sequestration in longleaf pine? I think what he's trying to get at is how long is that versus the more short-term approaches that might, for instance, sequester more carbon more quickly?
Okay, yeah. I'm going to pull some numbers out of thin air. There are situations, first of all, where longleaf pine in drought with the prescribed fire can be sources of carbon. So I would say your bottom range number is 0, okay, in a bad year. In a good year, you're probably talking, and I'm going to give this in, I think it's grams per meter squared per year, 150 to 200. And I think long-term, you might be talking about somewhere in the 100 to 150 grams. That's kind of off the top of my head. I would suggest a paper by Flanagan et al. In, I believe it was Ecosphere, about 2017 or 18, that has some simulation modeling that actually looked at carbon gain and loss over a 100-year time span. And basically by the time I think you get to about 50 years, your longleaf is doing a little bit better job in terms of carbon sequestration. Now, just to put that in perspective, that 100 to 150 grams per year, if you look at a really good year for something like loblolly or slash, you can easily get into the 500, maybe 700 or 800 grams in some sites, which is just tremendous. It's loblolly, short rotation loblolly on a short term is right up there with tropical rainforest in terms of being able to sequester carbon year over year. But yeah, I'm thinking about 150 grams per year.
Thank you, Stephen. Next question is from Adam Komar, who worked for Matt Herto on Fort Benning, looking at some carbon storage up there. I guess that was with Lisa Samuelson and her lab. Basically saying that the frequent burning they felt was compromising the ability of the forest to sequester carbon, and it really wasn't particularly great for this forest type. But really just wanted to ask, what do you think the role of frequent moderate intensity fire on carbon sequestration and water yield might be?
Well, I mean, on carbon sequestration, sure, anytime you burn, anytime you're removing biomass, you're putting CO2 into the atmosphere, as a fire manager, as a land manager. I think you have to weigh that against the long-term risk of fire or long-term risk of beetles or storm damage, or even competition within the forest itself. I think by reducing competition through prescribed fire, you can have healthier forest. It may be, I don't know what the specific situation was at that site, but I don't think every site needs to be burned every 2 years. Some sites might need to be burned every year, but I think you need to consider the fire return interval, up to 6 or 7 years, maybe for like a dry site. We have some fire exclusion sites here that have been without fire for 20 years now. And one of those sites is on a very, very sandy, sort of sandhill type ecosystem. And it would be tough to argue that that site has really gone to the point where it absolutely needs to be burned to maintain longleaf pine. There's actually plenty of longleaf pine in that. So I think for drier sites, you probably would have to burn less. In terms of the water yield, I think the burning, probably the more you burn, the better in a lot of ways, but you really just want to burn at a frequency that controls the hardwoods. I think some of the hardwoods that come into the understory, whether it be shrubs like wax myrtle or tie, if you're in Florida, or aggressive oak species like water oak or willow oak that tend to use a lot more water than longleaf, you want to burn at a frequency that you control the hardwoods. And I think that will have a big benefit for your water yield.
Hey, Stephen, I think we've got time for maybe one or two more. Question: do the measurements of carbon sequestration consider native grass plantings and the mycological community associated with longleaf pine and native grasses, or is that just too hard to measure with current technology?
Yeah, I think not to be facetious, but I think you'd really have to get into the weeds there to measure, every little piece of the puzzle. I do think that's where focusing on a technology like eddy covariance, where you're seeing total inputs and outputs of carbon at a stand scale. And by stand, I mean a square kilometer or half a square kilometer, has some benefits. Otherwise, I think you just have to look at long-term soil carbon trajectories. And I think that from my experience doing that, doing carbon work, if you can look at long-term trajectories, or maybe do a space for time substitution where you're using stands that have been restored at different times, as long as they have the same soil type, I think you can come pretty close just looking at standing soil organic matter.
Okay, we'll try one more and then we'll have to go. Eric Krieger, hello, Eric. Good to see you again. Is there any movement within the carbon markets to better recognize unique aspects of carbon storage in longleaf pine? It seems to call for a more refined protocol than the business as usual that's going on in the market now.
I can't say for sure that there's movement within the markets, but I do think the science is getting out there. And I think there's more and more consideration that below ground processes need to be accounted for. Some of the programs that I've seen presented at least accept that 50% or more of the carbon is below ground, and so that their inventory figures, whether it be from remote sensing or from timber cruising, will account for the fact that there is a significant amount of below ground carbon. For longleaf pine, I'm not sure that markets have recognized it yet. Again, it's only about 3 or 4% of its historic cover. So I'm not sure that it has become enough of an issue for those market-based sort of promoters to take into consideration. I think I present this today mainly as sort of an alert to be aware that you can manage your forest for water yield, but also that you have to watch out for the negative aspect of accounting for forest carbon sequestration, that you may not be able to sort of reap benefits from both types of programs. Hopefully that does change though.
Okay, it's 3 o'clock, so unfortunately I'm going to have to cut us off. And I want to thank you all for hanging with us, and thank Dr. Brantley for presenting today. And thanks Southern Regional Extension Forestry for helping us put this webinar on. So thank you all, and come back. We'll have Mike Connor on October the 12th, 13th. I can't remember which, but please join us again for another Jones Center webinar. Thanks.
Thank you.